Hey everybody, and welcome back from holiday break. We are starting a new unit today. So, this entire unit pretty much I'm saying falls under the heading of geometry, which is the field of basically measuring things on Earth. So that's kind of these two breakdowns here. Geo meaning Earth, and then METR meaning measure. So we're actually opening up with a relatively uh, simple concept that we've probably encountered before, but I want to basically do my due diligence here and make sure that you understand area equations, but also the derivation of them. So that's where they came from. And we're going to extend that into solving for some missing characteristics as well as just straightforward finding area of shapes. So on the pre-assessment that we had done before break, this was an area that, some folks were able to find success on and get the answers, but there was enough, not quite sure how to do this or things like that, that it definitely warrants going over. So I'm going to go at least with some assumption that we've seen some of this before. So it's not like I'll be treating this from scratch. So if you are in the group of folks that this is a little bit more difficult for, then I would kind of reach out. But otherwise, like I said, my guess is that we've seen it before to some extent, but we'll see what we can do. All right, so I'm going to go through each of these shapes and just kind of talk about how we can generate basically the area equations. And for rectangles, we almost need to go off the assumption that it's just area is defined as length times width. Okay, that's like our basic structure. So in a rectangle, we'll also add in some additional markings. So here we have 90-degree markings. You also might notice in geometry that we'll put hash marks, so like single strokes to represent the fact that those two sides are the same length. And then if I have a different pair of sides that's also the same length, then I would give those two stroke marks. Okay. So for rectangles, we really just have length times width in order to figure out the area. Squares, even though they're simpler, um, we might use a different equation for that. So if I just have basically an S and I'll use S for side length, what's a little bit different about the square is obviously that everything is the same length all the way around. So if I'm finding the area of this, I would do S times S or just S squared. And what makes this a little bit nicer is that if I have to find a missing side length and I'm given the area, I can do that with a square, but I can't do that with a rectangle unless I know either the width or the height. So that's kind of a key difference in those equations and why we would use area equals S squared versus, oh, that's just, length times width. It's the same thing as a rectangle. We don't want to lose sight of the fact that we get that added bonus that the sides are actually the same. Okay, so parallelograms. Typically, we would denote parallel lines with these like single arrows. So we know that those are parallel. On occasion, these are rectangles or are squares, but this is kind of what we end up having here. And for our area equation here, we need the base. So we consider this base, and then we consider this to be height. So area is just going to equal base times height in this case. And this really comes from, our rectangle situation, because this little triangle basically that we might be over accounting for here is the same as this triangle here that we're almost under accounting for. So that's why we can get away with just saying, oh, it's just going to be base times height. You'll notice potentially in some of the problems that I actually tell you the slant length of that parallelogram, but mostly that's just to kind of throw you off. It's unnecessary in order to find the area of this shape. So the important part about the base and height here, and whenever we see basically base and height, we want to think that they are perpendicular to one another or that they cross at 90-degree angles. Okay, triangles, we've talked about them a fair amount of time this year, so we probably don't need to go over it too much. But to find the area, we just need the area of this or sorry, the length of the base times the height. So we're going to say area equals, and this isn't my final area equation. We obviously need to make an adjustment. But if I just do base times height, and I kind of look back on this shape, what I would actually be figuring out is the area of this entire rectangle, which is really twice the area that we would actually want, right? This big, that blue triangle there offsets this triangle down here, so I want half of that. And then I have this triangle here, which offsets this. So that's why we end up with area equals 1/2 base times height. This is probably the most convenient form to see it written in. Obviously, there are lots of different options. We could say that this is base times height over 2, or something along those lines. Having it as 1/2 times the base times the height just makes solving a little bit easier when we get to that point. Okay, so a circle, figuring out the area of a circle, we would need our radius in order to do that. Half the distance across the circle, this entire distance obviously being the diameter of that circle. And to find the area of that, we do pi times our radius squared. Sometimes it becomes, confusing. People might mix this up with, let's say, the circumference equation, which is 2 pi r. And the way that I normally remember which equation is which is with that r squared. So if I kind of visualize on my circle, and you don't have to necessarily draw this on top of your own, but if I visualize what r squared is, r squared would give me the area of this shape, okay? Or the area of that whole square. And then it becomes a matter of, okay, well, if I'm trying to figure out the area of this entire circle, how many of those squares am I actually going to need, knowing that I already have this little bit of extra on here? And it turns out that we end up needing 1, 2, 3 of those, right? And then even if I scrape together all of this extra and try to fill up this last quadrant, I end up being a little bit short. And that's because we end up needing 3.1415, r squareds. We need pi r squareds in order to finish up that circle. So that's a good way to remember. If the only two things stuck in your head are area equals pi, or pi r squared and 2 pi r, in order to tell which one represents area, just go with the one that is r squared, because that's going to create an area for you. Okay. Regular polygons we'll probably hold off on for just a little bit. Regular polygon, if we just want to have the drawing down on it, and this is just something that I'd rather chat about in class. This would be basically a regular polygon. In fact, it'd be a hexagon. And that is a figure in which all the angles and all the sides measure the exact same thing. So if you envision, a perfect hexagon, stop sign, if you envision the Pentagon building being 5 sides and all the side lengths are the same, that is considered a regular polygon. And there's a pretty convenient area formula, but again, we'll probably talk about it on Wednesday. All right, trapezoids. So trapezoids take a few different shapes. So some folks kind of, might forget that this is a trapezoid, but also we can have kind of a more simplistic drawing, maybe where this is a little bit past 90 degrees. And in order to figure out the area of this, we end up again kind of looking at it in terms of a parallelogram, actually. So for any trapezoid that I'm given, you have this ability to actually flip it. Okay, so I could actually kind of flip it and tie it off with itself so that it looks like this. Okay, you can imagine just turning this and then sliding it over. And this, if we take a look, this is B2, B1 after I make this switch, and this is height. So if I'm trying to find the area of that combined shape right now, then that would be base 1 plus base 2 times the height, right? That goes right off of this parallelogram equation right up here. It's just base times height, but my base is actually the combined area of those two things. So I end up with this, and then, I did that initial doubling, which is something that I want to correct. So I end up with this as being my final area of a trapezoid equation. So 1/2 base 1 plus base 2, and then times the height. And there are different ways to kind of derive at that same thing. I just consider that one to be the most unique. Um, but you can do that with any trapezoid shape. So that ends up being our equation. I'm going to pause here. I kind of want this video to be in two parts. The next portion of this, I'm going to find the missing area of a few shapes and also find the missing measurement of a shape given the area. If you don't think that you need that video and you want to try hopping right into the worksheets, that's okay. There are two, and it's mostly just an option for you as to which one you feel comfortable taking on. I would like all the problems to be completed. It's area, so I don't consider it overly difficult, but again, email me if needed. And there's, again, also going to be a follow-up video if you're not feeling comfortable, just where I go through these problems. All right.